I made this video here to help you work through problems involving rolling where energy is going to be your best approach. So if you look at the diagrams that I've drawn here, imagine we've got some objects that are moving across a horizontal surface and they come to an incline of some kind. Typical question might be, how far up the incline are these things going to go? I'm not going to work through a whole problem for you, but I want to show you how to deal with an object that's rolling differently than how you deal with an object that's just sliding. So the object that's sliding, we've done these plenty of times. You're going to describe the kinetic energy that it has as it approaches the base of the hill, and that will eventually turn into gravitational potential energy once it's climbed up the hill. And the kinetic energy relationship is one that most students have an easy time remembering, 1/2 mv squared. And then we go from there with the conservation of energy. But this down here can be a little deceiving. Even if, let's call this a disk, even if that disk has the same mass and the same velocity, it turns out that a rolling disk has more kinetic energy than what it seems to have. And that's because, remember that when we talk about the velocity, we're only talking about the velocity of the very center, because every point on this rolling disk has a different velocity at a different time. So what we'd have to do is actually break this into tiny little chunks, look at the velocity of every little chunk, and add up all the little contributions to the total kinetic energy, the 1/2 times the little m's times the v squares. Well, that sounds like integration and calculus, and that's no fun. But it turns out that there's a clever little shortcut that gives you the exact same amount of kinetic energy. And here's how we do that. What we do is we treat rolling objects as objects that are equivalent to those with linear motion plus spinning motion. So if you imagine that this object here has its linear motion v, that means the entire thing, instead of rolling, is kind of sliding forward, just like the mass up here is. So we would have 1/2 mv squared if that were the case, and then they would be equal. But we have a little more energy contained in the rolling object, and we get that by imagining it's only spinning around without moving forwards. And we've described the kinetic energy of that as 1/2 I omega squared. So let's imagine specifically that we have a disk here and see what this turns into. So 1/2 mv squared, that would be regardless of shape. And then what we'd have to do is look on our table of moments of inertia and figure out what it is for a disk. I'll tell you it's 1/2 mr squared. So we have a half, and then a 1/2 mr squared, where r is the radius. I'll draw a little radius on here just so I can see that parameter. And then here's one of the important constraints with rolling. And I dealt with this in a different video. Maybe you've seen it, maybe you haven't. But when things are rolling, the angular speed that they have, that just accounts for its spinning motion, is related to the velocity of the center of that thing. And the relationship is that omega is v over r. So instead of omega squared, I'll put v over r squared. And now look how nicely this all simplifies. We have a 1/4, and then the r squared here in the bottom and the r squared here on the top, those both go away, and we have just a 1/4 mv squared. So I like to see that little term there because that gives you a feel for how much extra kinetic energy this rolling object contains, more than the linearly moving object above it that doesn't have the spin. It's actually 50% more. So that means if it has more energy at the bottom, it's going to be able to climb higher along the hill. And we could do the same kind of analysis down if we were coming down the hill. If we start something at the top of the hill and roll it down, some of that energy, you think, well, they're going to hit at the same speed, but that's not true because it actually takes more energy to roll an object than it does just to slide an object. I'm talking about down a frictionless hill. And so we find the rolling objects aren't moving as fast as their sliding counterparts that start from the same height. So clever little trick there. Again, just to kind of summarize, what we're doing is we're treating rolling as just a combination of forward motion without any spin plus spinning motion without any forward motion. And the two together give us exactly the same amount of kinetic energy as if we had analyzed all the little pieces and their individual kinetic energies. So hopefully that helps you when you approach your rolling problems, and good luck.